In this lesson, we'll talk about symmetry and then even and odd functions. And so we're just learning more ways to describe relations and functions. So we'll start with y-axis symmetry. And if you have y-axis symmetry, it would look like this. And the x values can change signs. The y values stay the same. And those 2 points will both be on the graph. If this is a function, then it's called an even function if it has y-axis symmetry. X-axis symmetry would look like this, and here we can see that the y values change signs, or can change signs, and then those points will still be on the graph. This doesn't have a special name. It's not a function, so we don't have that special name. Down here, symmetry to the origin, it would look like this, or here's an example where if we had positive x, positive y, we just go down and have negative x, negative y, and that point will also be on the graph. So we change both signs of the x and the y, and that new point will also be on the graph. And this is called an odd function when we have symmetry to the origin. Okay, so let's look at let's start numerically. And if we're going to make a table, it will be easier to isolate the y, subtract x, and then multiply by negative 1, square root, positive or negative, radical x minus 1. And now let's look at a table. So if we put a negative 2 there, we'll have positive or negative square root negative 3. And we put a negative 1 there, positive or negative square root negative 2, negative 1. And then down here we have 0. So these are all imaginary. They're not going to show up on our graph. Put a 2 in there, and we get 2 minus 1 is 1. So that's positive or negative 1. And here we have positive or negative radical 2. So out of these points, we have one x value, one y value, one x value, two y values, and the sign of the y value is changing. So if we have the y value changing signs, then we have x-axis symmetry. And let's just plot those points, and we can see x-axis symmetry. We have 1, 0, and then we'll go over 2, up 1, over 2, down 1, and we get a sideways parabola. So we see the x-axis symmetry. And then let's look at it algebraically. test y-axis symmetry. To test y-axis symmetry, if it's going to have y-axis symmetry, the x can change signs and we'll still have the same equation. So if I make that a negative x, and then we look at this and compare it, this is not the same as the original. So that was a test for y-axis symmetry. Now let's test x-axis symmetry, and we'll change the sign of the y and see if we get the same equation. So replace the y with a negative y, simplify it, x minus y squared. So it's the same as the original, and that means we have x-axis symmetry. All right. Pause the video and do the same thing with this problem. So if we put a negative 2 in there, negative 2 squared plus 6, it's going to be 4, negative 4, and we get 2. Continuing that, we'll have 2, 5, 6, 5, 2. And here we see the same y value with different signs on the x value. So if the x value changes signs, that means we have a y-axis symmetry. And if we graph the points, at negative 2 we go to 2, at negative 1 we go to 5, 0, 6, and we can see y-axis symmetry there. Let's test y-axis symmetry. To test y-axis symmetry, we make the x change signs. And that will be negative x squared. So if that's the same, then we must have y-axis symmetry. And we'll see in the next few examples, or in a few examples, it's also called an even function. All right, and pause the video, try the same thing with that. Graph, numeric, analytic. If we're going to do it numerically, we should isolate y. You don't have to use these numbers, but they work out pretty nicely. 3 divided by negative 3, we get a negative 1. 3 divided by negative 1, we get a negative 3. This is undefined. 3 divided by 0, 3 divided by 1, 3 divided by 3, and we see we have a negative x, negative y, positive x, positive y. Both x and y are changing signs, and we still have points on the graph. So if both change, then that means we have symmetry to origin. And if we look at the graph, left 3 down 1, left 1 down 3, and here we'll have right 1 up 3, right 3 up 1. And that will be symmetry to the origin, because if we have a positive x, positive y, and we switch it to a negative, it's also on the graph. Test symmetry to origin. To test the symmetry to the origin, we'll take the original problem, the original equation, change both signs, simplify, and show that when we change both signs, we still get the same equation, we still get the same graph, so that means it has symmetry to the origin, and it's also called an odd function. And then we'll use symmetry for this type of question where they ask, is a relation, or is a function even, odd, or neither? Is this function even, odd, or neither? And we just do the same work that we just did. We can look at it graphically, numerically, or analytically. So let's start with it numerically. Absolute value of negative 2 plus 3, we get 5. And here will be a 1 plus 3 is 4. 0 plus 3, 1 plus 3, 2 plus 3. We have the same y value, but we have opposite signs on the x value. So when the x value changes signs, we have y-axis symmetry. And y-axis symmetry is called an even function. Not everything with y-axis symmetry is an even function, because it might not be a function. Here it is a function, so we call it an even function. And that's just shifted up 3. We're starting at 0, 3. And the graph goes like that. We can see y-axis symmetry, and that's an even function. To test for even or odd, we can always just put a negative in for the x. Alright, if you substitute a negative x for the x, and we get the same thing, which we do here because it's absolute value, same as the original equation, means we have an even function. Alright. All right, pause the video and try that one. So here we're going to have -2 cubed plus -2, and we'll have -8 minus 2 is -10. Down here, if we did a 2 cubed plus 2, we'll have +10, and 0 gives us 0. 1 would be a -1, that would be a -2, and here's a 1 plus 1 is 2. We have -x, -y, +x, +y. Both x and y are changing, so that means it's symmetry to the origin, and here it'll be called an odd function. Oh, it looks like it's symmetry to the origin. With the points that we've chosen, we can say it appears to be symmetry to the origin. Let's put a question mark because we don't know for sure. It's symmetric to the origin. It appears to be that way. Let's look at the graph. Based on the points that we chose, it does look to be symmetric to the origin, and we could just say odd function question mark because we've only checked 5 points, and out of those 5 it is symmetric to the origin. Okay, so that looks like an odd function, but we have to check analytically by substituting a -x. And we want to know if we change the x, do we also change the y? Let's say this. If we change the x, do we also get a negative y value? So that's kind of a, can be a confusing way to read it or write it. We are just going back to the concept of you can change both x and y and you get the same equation. So if this ever confused you, you could always just write it with a y, change the sign on the x and the y, and then see if you get back to the same equation. Let's do it that way. That's the original equation. Let's see if when we change the x and the y, we'll get the same equation. And we will, because when we cube the negative, it's still negative. Multiply everything by a negative, and we end up with the same equation. We have, if we change the y and the x, we still have the same equation. So we get, we know it's symmetric to the origin. And that means it's an odd function. All right. If we're not going to write it this way, we need to do it in function notation. We could write it like this, and that would just be f of -x is -x cubed plus -x. And then we write it as -x cubed minus x, which is -x cubed plus x, which is -f of x. And that would be the way it's usually written in a book. We've shown that when we change the x, we also change the y, and that would be that, showing that it's an odd function. Okay, pause the video and try that one. So rather than doing all the points, we can just look at a few, because it doesn't work. If it doesn't work for 2 points, then it's definitely not symmetric. So if you put a -1 in there, we'll go 1 plus 6 plus 9. -1 gives us 16. And if you put a +1 in there, 10 minus 6 is 4. So right away, we don't have the same y value, and we've changed signs on the x value. So it looks like it might be, I'm going to say it must be neither. And if we factor that as x minus 3 equals 0, we know that the x-intercept is 3. And it's a parabola opening upwards, so we know that it's doing that. And we can see that it's not symmetric to the y-axis, it's not symmetric to the x-axis, and not symmetric to the origin. So let's see what it looks like analytically. If we have f of -x, if we put in a -x and we get the same thing, that will mean it's even. If we put in a -x and we get the negative of the original, that will mean it's odd. And if we don't get either of these, then it's neither. So let's start with f of -x, and then we're going to have -x squared minus 6 x plus 9. Let's see how it simplifies. X squared plus 6x plus 9. Can we make this, or is this, the same as the original? No. And if we factored out a negative out of everything, is this the same as the original? And that's a no. So this says it's not equal to f of x. It's not equal to negative f of x. So that means it's neither. Both of these, neither of these were met, so we know it's neither even nor odd. And we saw that occurring in the graph and the table also. And I'll stop there.